We're going to talk about local and global extrema. So we've talked about local extrema before. Sorry, we talked about global, like that absolute max, absolute minimum. So global maximum when a turning point in a graph is the highest point in the graph, period. A global minimum is when a turning point in a graph is the lowest point in the graph, period. It's not just for a small region. Now, local minimum is also a relative minimum, a turning point in the graph that is a low point but not the global minimum. And local maximum, also called a relative maximum, is a turning point in the graph that is a high point but not the global max. So in this figure here, we see a local maximum. Come on, my pencil fell asleep. Okay. We see this local maximum here, but the global maximum is over there. That's the highest of everything. This is a local minimum. There's no global min because it goes down forever. So let's look at this last example. Oh, it's a word problem. How fun. An open box, top box, is to be constructed by cutting out squares from each corner of a 14 centimeter by 20 centimeter sheet of plastic and then folding up the sides. So imagine here is our sheet, and where this is 20 and this is 14. So they're going to go through and they're going to cut out these corners. These are the square corners. They're going to fold on these dotted lines. So this becomes, that's x, that's x. This is x, 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 x. So this part here would be 20 minus 2x. And this would be 14 minus 2x. So we want to find the size of the squares that should be cut out to maximize the volume. So by the way, the image when you fold it up, I'm going to do my best to do a three-dimensional looking image. So it'll be something like that. So that this side is 14 minus 2x. This is 20 minus 2x. And the height here is just x. The height is x. So our volume is going to be x times 20 minus 2x times 14 minus 2x. So it's going to be let's see, x times, it's going to FOIL out first, 280 minus 40x minus 28x plus 4x squared. So it's going to be, distribute that through, 280x minus, I have a minus 40x and a minus 28x makes it minus 68. So minus 68x squared plus 4x cubed. So that's our volume in terms of x. I'm going to rewrite this as 4x cubed minus 68x squared plus 280x. So we wanted to, I guess, graph this and see where our high points are. So if we graph it, we get a graph like this, and it really wouldn't make sense for x to be really bigger than 7, because that'd make one side 0. So yes, this would go up forever eventually, and this goes down forever. But what is meaningful to us are the values in this, with this domain. And so we have a peak value here, which turns out to be x at 2.75. That corresponds, and using like Desmos, 2.75 is our x. So that gives us the maximum volume. So the volume at 2.75 for x would be around 339 cubic centimeters. And that's it.